Yeah, good evening, everyone. Thank you for having me here. So I'm Vishnu. I just moved to Orlando like a few months ago and excited to be part of Python group. So yeah, I work as associate technical lead at Core AI. I primarily work with um, building and deploying AI models and AI agents for enterprise specific use cases. Most of the ML platform and models that we built initially started out with Ray. That's why I'm sort of excited to talk about Ray and show everyone what it's capable of and how to leverage it. So yeah, with that, let's talk about Ray and how to deploy models at scale with Ray. So yeah, we're gonna the talk is gonna be in this fashion, like why Ray and then what is Ray and how does Ray work and some primitives and features of Ray and how does Ray work with Kubernetes and the whole deployment architecture. Right. So Ray started out as an open source project from UC Berkeley Rise Lab, and now is maintained and developed at any scale, but it's still an open source project, kept out with many developers working on it. It's basically a unified framework that is used to scale Python and AI workloads, and it's mainly useful because for using Ray, you don't have to know or be an expert at distributed computing. Ray automatically abstracts and handles all the orchestration, scheduling, fault tolerance, autoscaling, all of that. And and it also has rich set of libraries, especially targeted at machine learning workloads like pre-processing, I mean, data pre-processing, training, tuning, RL, inferencing, and serving, all that. So, oh, yeah. So, yeah, all of it is good, but how does Ray do all of it and how does it work? Um, we can start out by talking about the basic primitives and computational units that Ray offers. Um, to make this all work. The first one would be array task. It's basically the basic unit of computation in Ray, and it's abstracted or given out by using a decorator called ray.remote and sorry, ray.remote. And basically what this decorator does is takes in any abstract Python function um, and makes it a designated remote object by returning a futures, which will basically give you an object ID that is mapped to the result of your function. And eventually you can fetch the result once the task is executed. Um, you can get the result by just doing a dot get. You can instantiate a task by using dot remote, and basically what it does is it puts in an execution queue whenever you do a dot remote on a task, like just say the name of the function is my task and you did a dot my task dot remote. It returns a features object and puts the actual task in the execution queue, and once the execution queue is done, it pushes the result into a data store object. Pushes the result object into a data store, and you refer to the result by the object ID. So yeah, it's stateless, it's parallel in execution, and it's easy to use. That's the basic. And then you have reactors. Reactors are nothing but remote classes. Ray tasks are nothing but remote functions. Reactors are nothing but remote classes. Basically, you can by class, therefore it is stateful, and you can define any number of methods within the class that all becomes methods that are accessible by your reactor. And uh, you can instantiate a class by just doing a dot remote, just the way you did with functions. But the thing here is that whatever methods you're going to call on top of this remote class, I mean the actor, are sequential in execution, and they are also stateful in the way they execute. So which means they share the mutable space of the class whenever they're being called, and eventually you can get the result back by doing just dot get the same way you did with the functions. The next one is ray objects. Ray objects are nothing but the results that are returned by the ray.get, be it the class objects or um, just the tasks. So whenever yeah, like I was saying, like whenever you do a dot get, which means the task is finished executing, so you pull the result from the shared data store or shared memory. uh, Likewise, whenever the task is being executed and before you do a dot get, the result is also being pushed to the data store. So that's basically objects. Objects in Ray refer to data that is stored in the distributed object store. That's all. um, yeah, so these are like the primitive features or concepts of Ray, but how these all come together to um, work is um, like you can see that in here with a Ray cluster. So Ray cluster is basically a combination of a head node and any number of worker nodes, and a head node basically consists of a worker node. It can have a worker. Oh yeah, well, basically we can go to worker first. So workers are basically where your application runs. So these are the place where actual code that you wrote gets executed. Now head can also have a worker, which means it can technically execute your application as well, but that is not its main purpose per se. It has something called as a driver, which is a specialized worker that basically executes your like main function, or like the underscore main class, that function that you define usually. And yeah, Raylet is basically present in all of the nodes, and Raylet is a thing that manages the shared resources of that node. So and specific to head, you have GCS, Global Control Store, which is basically array level metadata handling store. So all the metadata, all the logs, all the info, the fault tolerance related info, all of it is being controlled and stored at GCS level. Um, yeah, this basically explains what I said. Like, yeah, worker as associated a worker is associated specifically with a job, and it has its own ownership table, or like yeah, two ways. Like either if the results is finished and you have to store the results, it pushes it to the ownership table to get the reference location of the result, or it sometimes also has an in process store to just store those smaller objects. And yeah, Raylet is basically a shared memory object store, which basically controls the controls the shared node level resources. Yeah, and GCS is that, and the driver process is the one that executes the main function. Did I miss something? No. Yeah, that's the whole architecture of. And yeah, so basically the way Ray functions whenever you call a dot remote is by putting all of your executable tasks into a dynamic task graph. Like it constructs a computational graph, and whatever tasks that are need to be executed sequentially would be like, let's say you have the output of task A that needs to be consumed to calculate object B, then it first executes A and then comes to B. If you have something parallel, it parallelizes them and then comes to the second sequential step. So it does this through the dynamic task graph. So yeah, to summarize, you submit a task to the driver, and the driver makes a remote call to see which worker can optimally execute your task. That's the scheduling. And once it's scheduled on on a optimal worker, then the task will be executed there, and then the result will be stored in an object storage, and result will be retrieved later on using the references, and then the task is completed. If there's an error, then in the whole cycle, if there's an error, then it just refers to the error. So Ray has like I said, saying Ray has like rich AI libraries that are specifically designed for AI workloads, like data and data preprocessing, training, tuning is specifically for like yeah, training and tuning are specifically for either your pre-training or fine tuning, and serve is for inference, and RLLib is for specifically for RL related workloads. So Ray Core has all of the primitives we spoke of, like tasks, actors, and clusters. And on top of them is what these libraries are built out, and you can interact. I mean, these libraries can interact with cloud services like either like a VMs of AWS or Kubernetes, just Kubernetes on-premise version, um, using some bridges like Kuberay. So yeah, so now we know how Ray works, but so why do we need to have Ray work in hand with Kubernetes? So Ray provides the unified Python experience that all data scientists love, like to prototype fast and um, make multiple iterations of your experiments. But the operational benefits are being provided by the Kubernetes. So whenever you want to deploy your um, ML workload at scale in production, usually the de facto way these days is to go with Kubernetes or a Kubernetes inspired or styled deployment. Um, so combining Ray with Kubernetes offers you that unified Python experience with the operational benefits of Kubernetes. So yeah, I wouldn't go much into the Kubernetes architecture, but on a high level, whenever a request is submitted to the control plane of the Kubernetes, the way it works is to try to match the desired state of the system with the actual state of the system and bridge the gap between them. The fundamental unit of scheduling in the Kubernetes is a pod. And pod contains multiple containers. Containers are instantiated images, instantiated Docker images, and multiple pods together can comprise of a Kubernetes node, and multiple nodes together combine of a Kubernetes cluster. So so the thing is, Kubernetes knows when to schedule. It deals in pods, so it knows when to schedule a pod or how to schedule a pod, but it doesn't know how to schedule a say a Ray cluster or a Ray actor for that matter. So so how do we bridge this gap? So we do this by something called Kuberay. Kuberay is a operator that basically sits on Kubernetes with extensions of some custom resource definitions, and it interacts with Ray features and Ray native objects, um, and also interacts with the Kubernetes. So the Kuberay now essentially knows how to schedule Ray clusters and um, the Ray pods. So yes, Kuberay basically consists of three custom resource definitions. These depend on the kind of workload that you would want to interact with, but mainly has three, which is like Ray cluster, Ray job, and Ray service. So Ray cluster is typically useful when you want a persistent job that is going on and you want to interact with it, debug with it, um, and uh, and know like information about it like while you're trying it out. So it still has autoscaling and fault tolerance, but it's mainly used for like interacting and debugging. Ray job is when I would say it's mostly used like when you have multiple teams like or multiple people use trying to submit jobs like training jobs for example, and you just submit the job, and the Ray cluster will be put in a queue, and then the job will be put in a queue, and then eventually it'll be executed in a Ray cluster, yeah, and gives you the results back. So these clusters are like recyclable here, and like multiple teams or people can try to use them. Now, Ray service is more on the inference side of it, like in the production when you don't want any downtime and you want high availability, that sort. Yeah, the three of them are used in three different use cases. But essentially, Ray cluster is common among them, and Ray job has like is a mixture of Ray cluster plus jobs, and Ray service is a mixture of Ray cluster and Ray serve. We'll see like like we saw already what ray cluster is of, like with the head nodes and worker nodes. We'll see what ray serve is in a bit, and how it helps in the fault tolerance and high availability. So yeah, so when we already saw how a cluster operates, but then how does it operate in a Kubernetes setup? So all the configurations in Kubernetes are handled by YAML manifests. So in the same way, you would need to define a manifest for your array cluster, which usually is fixed or like is instantiated, and then you get the array clusters. So the main things would be to have the specifications of head pods and worker pods, like what do you want the minimum number of replicas to be for the workers, and what should be the maximum replicas, like. And then you have some parameters you can define that that ensures this scaling happens between these minimum and maximum replicas. And then you will give some standard things like image paths and docker image files and etc. We'll see a bit more on what these parameters are that especially affects the auto scaling in a bit. But yeah, usually these are the main things that you would define in the cluster config for the ray cluster. Right. So talking about auto scaling with Kuberay, it mainly happens at three levels. So applications like ray serve especially has ways to whenever the volume increases of the like the workload volume increases on your application, let's say you employ Reserve, it can automatically detect and um, increase the number of ray actors. In this case, basically worker nodes, increase or decrease the worker nodes based on the load. Now, how Reserve does it, we'll see probably in the next slide. Yeah, but it can do that. So that's the first level of auto scaling a tray based on the workload, determining or like basically upscaling and downscaling the actors or ray worker nodes. And then the moment ray serve submits saying that, hey, I need another actor performing the task, then kicks in at the ray worker node level, which is basically the array node level. So that to place an actor, you would need array worker node. So that's when the array cluster kicks in and tries to bring up another, let's say, array worker node. Now, if the physical machines like the VMs are sufficient, that's okay. But if you don't have enough actual physical machines to run the actors and the nodes, then Kubernetes kicks in and does an auto scaling of bringing up another machine with so and so CPUs or so and so GPUs, depending on what the request is, and then allocates a physical machine upon which Kubernetes pod sits in, within which array node sits in, within which array worker sits in. So that's three levels of auto scaling that can happen with Kubernetes and Ray. Now the first part where Ray serve um, like dynamically scheduling or like upscaling or downscaling the array actors based on the volume of the incoming requests. Now, how does that happen? We can see that here. So the blue lines are inference requests, right? So the basic components here are the serve handle, which is basically let's say the incoming requests, the interface between the user requests and your ray cluster. For example, that's let's say a serve handle. um, and then you have a head pod, and then you have multiple worker nodes. So this head node has uh, a few components in it. One is a HTTP proxy. This is straightforward. It basically accepts the incoming requests. It acts as a proxy, distributes it to the workers in a round robin fashion. And controller and autoscaler are basically where this storage of metrics of the, like, let's say the volume or the traffic happens, and based on which it tries to either upscale or downscale the replicas. So basically periodically all the replicas and also the serve handle pushes metrics on what is the number of requests, like the traffic, the number of requests that are being handled across these worker pods, and as well as what is the incoming traffic. So all these metrics will be periodically pushed to the autoscaler. So this is the red lines, you see that the stats that are being pushed. And also uh, the serve handle will keep polling if there are any new worker replicas. So if there are any new worker replicas, it tries to um, send in more traffic to the system. And uh, mm, yeah, so whenever autoscaler identifies that the incoming volume is not being handled by the existing workers, it tries to um, submit a request to bring up another replica, and that will be eventually polled by the serve handle to actually route the request. Now we can also talk about fault tolerance a bit here, like for example, yeah, obviously the workers are being handled by the autoscaler. In order to bring a worker up or down, autoscaler does that, and autoscaler sits inside the controller. If at all for some reason controller or autoscaler goes down, the ray head, it tries to restart the controller. If at all a HTTP proxy dies, controller tries to restart the HTTP proxy, and within that moment, like the duration where controller take to like restart and bring up the HTTP proxy, serve handle can directly communicate with the worker replicas as well. So that's why there's a direct link from here to the workers. It can either communicate it to HTTP or gRPC and directly bypass the proxy to send inference request to the worker. And once this is recovered, the metrics will be again like pushed to it. Now, uh, if the controller dies, Ray takes care. If HTTP, if Ray head node itself dies, then the cluster will try to restart and spin up a new head, within which, like I said, if there is no proxy, then there is no head node, then there is no proxy, then the serve handle can directly communicate with the worker uh, pods as well for that momentary duration. So that's briefly about fault tolerance. Um, oh yeah, so like I was saying, autoscaler tries to see the incoming requests and what is this request being served by replicas, and tries to decide if it should spin up a replica or not. But actually the way it does, or how does it compute that, is based on two parameters. One is target ongoing requests and the other is max ongoing requests. So target ongoing requests is basically at replica level, how it's a configuration we give in the cluster config preset, and it's a number which we want each of the replicas to handle, and this number is usually derived by what is the desired latency per request that you want, and what is the number of requests that you're getting like in a duration. So that decides how many target ongoing requests, like how many requests can be there at a replica level. um, and all ray cluster tries to do is, or basically controller and autoscaler tries to do is, to ensure that each worker that target is met, basically. So um, yeah, so serve attempts ensure that each replica has roughly that number of requests being processed and waiting in the queue. Yeah, the thing is, there are two queues here. One is a queue at proxy level, and then there is a queue at worker level. So when you say, when you calculate the response time of a request, you would essentially calculate the time the request sits in the queue plus the actual time it took to execute. So that time to sit in the queue can again be divided into two parts. One is the time it sits in the proxy queue and the time it sits in the worker queue. The reason for this is proxy respects at each worker level, there is a max ongoing request that is being set. That's the second parameter. And proxy basically respects this number, and it and if at all the max, like the ongoing request, crosses this number, then proxy holds off. It doesn't even send to the any of the replicas. What it does is it spins up the new replica and then diverts the traffic there, so that the new worker can serve this request. So to optimize this, basically the objective here would be to optimize these two queues. One is at proxy level and one is at worker level. So 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 for that reason, you would ideally want to set the max ongoing request, which is what you want at max queue in the worker, like slightly higher than the target, which is the actual what you want being executed at the worker level. So usually in practice, I find like it's 20% max ongoing request can be higher by 20% to the target ongoing request. Um, yeah, so if you set the max ongoing request too low, it basically limits the upscaling. But if you set it too high, it would be like aggressive upscale plus an imbalance in routing, because you have more replicas sitting there, or it'll try to spin up more and more replicas, and hence imbalance the routing. Um, yeah, to summarize up, um, whenever you whenever the traffic comes in, so first is received by the proxy, and then it tries to distribute it to the replicas. As long as it's less than the target ongoing request, we are good. It can handle more requests as well, and there is no queue at proxy or the replicas. But um, the moment the ongoing request reach the target ongoing request, this means that a queue starts piling up at the worker levels. So it starts to spin up a new replica, but there is still no queue at the proxy. The queue is only at the worker level. And now let's say your load is even increasing momentarily or at once, or for some reason your ongoing request became even more than the max ongoing request. This is when you will start to see the queue at proxy and the queue at workers. Now the serve will still try to spin up new replicas, but it'll try to spin up new replicas in such a way that it will clear the queue at the proxy first, and then eventually at the worker level, and then eventually it tries to balance the load across all. The reason this is probably important for ML workloads is traditionally Kubernetes can also do this upscale downscale, but it does so using it does so with the criteria of CPU utilization or RAM utilization. But for ML workloads, it's either with requests or with GPU consumption. Both of them are not native to Kubernetes autoscaling. Both of them are um, treated as like non-native resources. They are custom resources. They are not native to Kubernetes auto-scaling mechanism. So either if you want to monitor, yeah, so Ray also does monitoring at GPU level and request level. So that's why this type of auto-scaling is important, and that's where Ray can help out. Yeah, the last thing I want to talk is dynamic request batching. So Ray, um, yeah, so the this is all about how do you efficiently serve whatever spoke so far is about how do you efficiently serve one single request. Like the optimizing parameter here is like how like minimize the queuing time of a request, both at proxy or basically the queuing time. But let's say you have multiple such requests coming in concurrently, not sequentially, but concurrently. Then how do you optimize? Ray has a way to do that by using something called dynamic request batching. What it does is it you can set a like there are two parameters here. One is max batch size and the other is batch wait timeout. So the timeout here means that the serve handle is going to basically wait for this, let's say here it's zero 0.1 seconds. So it's going to wait for 0.1 seconds, pull in all the requests that comes in this 0.1 seconds window with a maximum cap of 8 because we set max batch size as 8, and bundles all these requests as a single batch and sends it to your application. And once these 8 requests are served, the application sends the results back to the serve handle, and the serve handle like decouples and sends the results back to respective request user like source. The reason again this becomes significant with ML workloads is because with ML workloads we can do parallel computations. I mean, like, yeah, like matrix multiplications and batch inferencing. So with you don't have to serve one request at a time, but you can serve like a batch of requests with like a minimal overhead when compared to like serving one after the other because of GPU parallelization. So that's why dynamic matching is another step where another area of optimization where you can try to reduce the latencies. Uh, yeah, that's it. Any questions? Feel free to ask. No. Okay.
Well, while other people are thinking of their questions, and put any questions you have in the chat if you don't want to speak on the recording either. So it's clear that this can scale up to very large systems. There's a once you get once you get Kubernetes involved, the scale of the ops really starts increasing. I'm curious because we started with Ray and Ray working within the Kubernetes nodes, how easy you find Ray to get started with, because I remember uh, almost a decade ago, the first real friendly, easy to use parallelism in the Python data science and machine learning space was Dask. And I know Dask is still used all over the place. I'm curious how comparable you find Ray is to Dask in both its scalability and its easiness to get started with, or do you think that they're really trying to achieve different things?
I haven't personally used Dask, so I don't know the comparison, but I can speak for the ease of use of Ray because like at work, like for over a year, we built our custom like deployment and fine-tuning pipelines using Ray. So, and I was like mainly involved in doing that. And as like when I started out, I do not have any knowledge of distributed computing, and I was able to pretty quickly like even during prototyping, not like building any pipelines, even during prototyping, I was able to quickly assemble like 2 3 laptops and run a program like run a machine learning like a training job on like multiple laptops, like distributing the workload. And yeah, because it's I guess because it's open source and like there are a lot of people actively working on it and developing in it, like there's rich white papers and documentations and all that, so it was pretty easy to use. And also it's all abstracted. It's like writing just Python code, like it's really abstracted and easy to just use that. And from a scaling perspective, yes, it can really scale up when you like you said, when you involve Kubernetes in it, it scales up like really well, like because we are using it in production as we speak. And yeah, so that is always there. um but yeah, I always found like Ray is the friction between like you as a data scientist like prototyping something and pushing it to production. The friction between those stages is like very less when we use Ray, because the say everything is in place even while you're prototyping, so all the scaling and fault tolerance, everything is taken care even at that stage, so you don't have to do a lot of ops work um, when you transition from the first stage one to like to production.
I know one of the things coming from an enterprise, enterprises have access to a lot of tooling, both in the cloud and on premises. But let's say we're working on this outside of a out of an enterprise that has a lot of money in order to handle these requests and these servers. How easy is it to get started locally on your machine to uh, I don't have as much experience trying to run Kubernetes locally. It's been a while. Uh, but how much of your time when you are developing do you think you're spending trying to get Kubernetes set up initially? And uh, because Python, I love how Ray is using the decorators. Decorators make a lot of complex things really easy for the developer to implement.
Yeah.
And we do love really short hello worlds for our libraries. But once you involve Kubernetes, there's not really a short hello world to get Kubernetes set up. How for someone who hasn't used, say, Kubernetes before or any of the parallelism, how easy is it to get set up in that regard?
Yeah. I mean, yeah, that was me. I haven't used Kubernetes before starting out with Ray. Um, so I guess there is some initial learning curve, especially in Kubernetes, like you said, if you want to use Ray with Kubernetes directly. But when I started, it's like just using Ray was like relatively easier than like using Ray with Kubernetes. And I did start out locally, like just assembled 2, 3 laptops and try to do a distributed computing over them and using just the internet and some friends' laptops. So yeah, the toughest part is to set up Kubernetes locally and try to have all the Dockers in place and a lot of issues were to um, just the versionings and all that stuff. So um, I think the learning curve would be mostly at that place with the use of Kubernetes. Like I think once you get once you get like used to that, it's really straightforward. If someone is already in ops, it's like really easy for them. But if someone is just starting out with ops, um, it's relatively easy if you're using Ray first and then Kubernetes with Kubernetes with Ray, rather than directly jumping to like Kubernetes with Ray.
Yeah, I know we enterprise loves the term DevOps, and so do startups, especially because if you can get one person to do two roles, but they are so far apart. It's anything that can make it easier to try to integrate the two is worth its weight in gold, especially for a DevOps engineer.
Yeah, it's now called MLOps. So
So thank you, Vishnu, for talking about building ML pipelines.
yeah, no problem. Thank you for having me.
Absolutely.